So the first one, it says 3 stages of thunderstorms. So that was like one of your quiz questions. So cumulus, mature, dissipating. And remember, cumulus has an updraft. Mature has updraft and downdraft. And the dissipating has only a downdraft. So the next one says, so kind of know this figure right here. This, of course, this is a mature thunderstorm. Be able to, on the figure, identify the updraft and the downdraft. And remember, with the downdraft, we said it can create this gust front. So it's hard to see, but the gust front is actually kind of right up here. Because it's raining, that's the downdraft, and the gust front is the wind in front of it. Okay?
So it's coming from this way?
That's inflow, but the gust front is going out that way.
Oh, going out.
Mm-hmm.
Okay.
Gust front is going out. And then remember, you can get that thing at the top, that's called an overshooting top.
The overshooting top.
Yep. And then the anvil, didn't say it, but, so where's the anvil here?
Right below the overshooting top. It's
Right,
the flat
exactly. Mm-hmm. The anvil is that flat top part up there. Exactly. Yep, you got it. Shelf cloud is this right here. This kind of thing that juts out. That's a shelf cloud. Wind shear. Wind shear is, as you go up in elevation, you're either changing the speed or the direction that the wind is blowing. So to kind of show it's going faster and faster, I have those long lines. Okay, so that would be strong wind shear. And yesterday, and it makes these tilted thunderstorm cells. And yesterday, I kind of saw a little bit of that in the clouds, I thought. And then we talked about 2 weather systems that basically you have more than one cell going on. So the first one is mesoscale convective complex, and I have the word blobby. It's blobby. So each one of those little circles is a thunderstorm. Okay, mesoscale convective complex, blobby. They can be about the size of a state. I mean, that's a big weather system with a bunch of thunderstorms, and it moves. And then this one is a squall line of thunderstorms. So this one over here on the right, you can't see it, but the black again are the thunderstorms, tops of thunderstorm heads. And then you can see maybe it's like cold front doing the lifting. A squall line of thunderstorms. And I don't have anything for the next one, but supercell, TS stands for thunderstorms. So supercell thunderstorms bring severe weather. That almost sounds like Sally sells sheep cells by the seashore. So supercell thunderstorm cells bring severe weather. And then the next one is a multiple choice question. I don't like to necessarily get into the nitty and gritty of lightning, but just know that the terms leader, flash, and stroke all deal with lightning. Multiple choice question. And then thunder basics, I actually kind of brought in this upper right hand corner, I brought in what we know about thunder. And thunder is the audible part of lightning, and thunder happens because as electrons go from one point to another, they heat the air, and it's heated, and the air expands faster than the speed of sound. And let's see, and then kind of at the bottom of that slide, it talks about that the visible part, the lightning part, can get to you before the sound does. So there's a delay between when you see it and when you hear it.
Sorry, I thought you said 10 minutes.
Oh, sorry. And then goes to the next one. Actually, if you can count that delay, the number of seconds, if you divide the number of seconds that's delay between the flash and the thunder, you divide it by 5, that gives you miles. So if there's 15 seconds delayed, 15 divided by 5 is 3, so 3 miles away. If it's like 1 second delay, then that means 1 divided by 5, 1/5 of a mile. You're like, oh my goodness.
Too close for comfort.
Too close, way too close. And then kind of related to that, when it comes to the thunder, sometimes it's like really sharp, kind of a clap. And that's because it's just close and it doesn't have time to bounce off of anything. And sometimes it just kind of rolls, and those are kind of fun. That's kind of relatively far away. It's echoing off of objects. So speaking of far away, then we talked about heat lightning, which heat lightning is basically a lightning event that's happening too far away for the sound to make it to you. So the sound dissipates before it gets to you. And then we talked about wall cloud. And wall cloud are associated with, wall clouds are maybe the little bit of a cloud that will drop down from a cumulonimbus cloud to give you tornadoes. And a funnel cloud is like a tornado, but it doesn't reach the ground. And then Tornado Alley, that video we watched on hurricanes, there's a hurricane alley. I never knew that. So Tornado Alley, though, is hotspot for tornado activity. And then we classify tornadoes not by the Fujita scale, but the enhanced Fujita scale, or EF scale. And they're classified from, I think there's an EF0. I need to look that up. But let's just say EF1 to EF5. So category, and F5, EF5 is the strongest type of tornado, and it's relatively rare. And the EF1s are relatively common, but they don't bring a lot of fatalities. And then went on to the next chapter, hurricanes. The deadliest hurricane ever, Galveston, Texas, 1900.
You didn't know the year?
Uh-uh.
Okay.
And then for the next one, I brought in a map. Of course, tropical cyclones, we call them hurricanes, but if you're in the Japan area, you'll call them typhoons. And if you're in Australia area, you'll call them cyclones. And then the anatomy of a hurricane. Of course, you have that center, and it is relatively calm in the center. So you have your eye there. Around your eye, you have your eye wall, which is kind of a bunch of little thunderstorms around the eye. It's the fastest winds. And then you have kind of branching off from your eye wall, your spiral rain bands. And then 4 stages in the life of a hurricane: tropical disturbance, tropical depression, tropical storm, and then tropical cyclone. And then kind of before tropical disturbance, for the type of hurricanes that hit our east coast in the eastern Atlantic, they ride these westerly waves. Westerly waves, darn it. They come from the east. They ride these easterly waves that are part of the Hadley zone, easterly trade winds. Kind of, they start out as little clumps of thunderstorms that become organized. Hurricanes can be upgraded if they pick up energy. They'll be downgraded if they lose energy. Of course, they gain energy, like, for instance, moving over warm water, and they lose energy, for instance, moving over land. And then speaking of movement, here's a figure from your textbook, and each line is a different hurricane, and it shows the paths of hurricanes. That H there is the Bermuda High, that semi-permanent high between the Hadley and the Ferrell Cell. And of course, we know that movement around high pressures in the northern hemisphere are clockwise, so that's kind of all coming together there. Rules to naming hurricanes or tropical storms. So remember, tropical storm is when it's first named, and it says each ocean basin has its own set. The second one is that at least our ocean basins around North America alternate female, male, female, male. For the eastern Atlantic anyway, they don't use names that begin with Q, U, X, Y, and Z. The next one, if they run out of letters of the alphabet, they'll run to the Greek alphabet. The next one is that there are 6 lists, kind of like we saw in your textbook and lecture. They kind of go to the next list for the next year. If a hurricane is specifically damaging, the name can be retired. So the 3 conditions required for a hurricane to form: nice, warm, toasty water. Need to have a little bit of twist coming from the Coriolis force. Bless you. That second criteria is why it can't be too close to the equator, because you won't get the Coriolis force spin too close to the equator. And the third one up there is you need to have unstable atmosphere. And we talked about how wind shear actually can get rotation started, can make your thunderstorm cells more stronger. But wind shear, when it comes to hurricanes, actually work against hurricanes. The next one, measuring the strength of a hurricane, goes on while the hurricane is doing its thing. They can actually measure the winds real time using those reconnaissance airplanes and dropping those drop wind sounds. It's like the opposite of a weather balloon, going down instead of up. Destructive forces of a hurricane include storm surge, tornadoes, and flooding. So storm surge in blue up there is that wall of water that happens as the ocean hits landfall. As the hurricane hits landfall. Storm surge. Tornadoes are embedded in especially the eye wall and the spiral rain bands in the thunderstorms. We would be most affected, if we are going to be affected by a hurricane, by large amounts of rain that it brings in the spiral rain bands and floods. The last one, the National Hurricane Center in Miami, Florida, are the folks that are coordinating the tracking effort and disseminating watches and warnings. So then, on to today's lecture. Actually, a little bit of Monday and then finished up today. Those initial conditions at the surface are great sources are those ASOSs, Automated Surface Observing Systems, usually located near airports, ocean buoys, airplanes, satellites. I'll give us initial conditions. 2 types of satellites. There are the relatively low polar type orbiting satellite. Has a kind of a small swatch. It's great for the poles, not so good for the mid-latitudes. And then we have the ones that are stationary, the geostationary ones. They're centered on the equator and they get larger swatches as they orbit the Earth. And they're stuck in one spot. So they're higher up, so you can get at least less detail. But the second one, the geostationary ones, are great for the over the equator, the tropics. Types of weather satellites, the types of pictures they take: visible, infrared, and water vapor. Remember, infrared is thermal. Numerical weather forecast. Those are the ones where you use computers. And at the top there, I kind of tried to show you kind of that piggyback of what they do. They use your computer, which has a model. You put in your initial conditions. Your initial conditions spit out a forecast for not very far in the future. Then you take that forecast and put it back in as initial conditions and kind of piggyback into the future, or kind of leapfrog, I guess I should say, into the future. Climatological forecasts use the kind of a 30-year average to estimate or forecast what the weather's going to do for a general region, general time of year. Analog approach was where you find a similar day with similar conditions of the atmosphere in the past, and whatever the day after that ended up being, that's actually what you would forecast the weather to be. Nowcasting and trend forecasting go together. Basically, for instance, here in the mid-latitudes in the Ferrell cell, we know that our weather systems generally come from the west, so we kind of use that as the trend. Nowcasting is trend forecasting, just even a shorter time period. Persistence forecasting, no computer required. Basically, what the weather is now will be what we'd say the weather tomorrow would be. And then ensemble forecasting, remember that was where we had kind of a big old matrix of lots of little boxes. Each one was a forecast with slightly different initial conditions. So basically you come up with a set and you look for a pattern, and then that gives you confidence in the forecast that you put forward. And finishing up, intuitively you would say that the longer the forecast, the farther it is away, probably the less accurate it's going to be. The shorter time frame that the forecast is, like hourly forecasts, are a lot more accurate than a 3-month forecast. And then last but not least, we talked about forecast bias. It means it's just kind of slanted always one direction. So what you hope to see in your forecast is that the error to actually be scattered on either side of what it really is, some high, some low. But if it's always low, for instance, then something's wrong with probably your model. So there you go.
What time did you want me to take the test? I've already forgotten.